All right. So we introduced quite a bit of notation and language, and I want to walk through an example that we have already seen to sort of process all those definitions. So I'll remind you some of the definitions again. So the setup is you have a ring R and an ideal I. Yeah. If you give me two elements A and B in the ring, I say that A is congruent to B mod I. That's how you read this thing. A is congruent to B mod I if the difference of the two elements A minus B is in I. Okay. And we showed that this triple equality sign, this is an equivalence relation. On R. And because it's an equivalence relation on R, it defines a partition of R. So it splits R into subsets, and these subsets are called congruence classes. A congruence class of an element A in R is it's just the set of all the elements of R such that they are related to A by this relation. So it's a set of all B in R such that B is congruent to A mod I. And it turns out that that's the same thing as all elements of the ring that are of the form A plus some element of the ideal. And a good notation for that set is A plus I. So A plus I, which means all these guys A plus X, X varies over I, happens to be all the things that are related to A under this relation, or we'd say these are all the elements of the ring that are congruent to A mod I, and it's called the congruence class of A. And then R mod I denoted the set of all these congruence classes modulo I. So this modulo I part we'll sometimes abbreviate. Sometimes I won't write that. So let's walk through a definition walk through all these definitions in the example of Z mod n. So the setup here would be, so let's fix an integer n, and then my ring R is going to be Z, and in there I have an ideal nz, means all multiples of n. Okay, so this means all these numbers 0 and n and 2n and 3n and minus n, etc. Okay. That's what nz means. It's also another notation for the same thing is parenthesis n, since the ideal generated by n. Okay, so this is an ideal in Z. In fact, we know that all ideals in Z look like this for some n. And now you notice that these statements are all equivalent. Notice saying, so let's take AB in I, AB in, not in I, in Z. Then saying A is congruent to B mod I means what? Means that the difference is in I. So these are the same equivalent statements. So let's say then the following are equivalent. A is congruent to B mod I simply means the difference is in I up here. That's the definition. But saying that the difference is in I just means, well, the ideal I is after all multiples of n. So the difference is in there means that the difference is a multiple of n. So that's same as saying that a minus b is a multiple of n. But that's same as saying that n divides a minus b, which we denoted by a is congruent to b mod n. So in this example, congruence modulo the ideal nz just amounts to congruence mod n, the thing that we studied in detail. These two things are the same in this example. Okay, so this is a very familiar relation for us, and we saw that it's a rather useful notation, useful relation to study divisibility question among integers. So if you want to be more specific, so a congruence class modulo I is same as a congruence class mod n. So a congruence class. So a congruence class modulo I is just a congruence class. The thing that we studied in detail again. So to be more specific, you can take n equals 5 or something. So I is the ideal 5z, all multiples of 5. Then a congruence class of 2, for example, is this thing, 2 plus I, which is same as 2 plus 5z, which means all these numbers. There's 2, there's 7, there's 12, there's minus 3, there's minus 8. That's a congruence class of 2. In our old notation, this was the thing that was denoted by square bracket 2. It's an element of Z mod 5. Yes, so this is the congruence class of 2. Yeah. So we say 2 is a representative for this congruence class. Right? Notice that the same congruence class, I mean this class, has lots of representatives. In fact, you can represent it by any element in this set. Minus 8 is also a representative for this congruence class. Okay, etc. Minus 8 is another representative. And indeed, the class of 2, which is this set, is the same as the class of minus 8. Because this denotes the set that you get by adding multiples of 5 to 2. And this denotes the set that you get by adding multiples of 5 to minus 8. And these sets are the same. It's that set up here. Okay. So I'll recall some of the things that we know about these congruence classes. Recall. there are 5 different distinct congruence classes. You can represent them by 0, 1, 2, 3, 4. So the classes were denoted like this. In the new notation, they will be called 0 plus I, 1 plus I, etc. You could explicitly describe them as follows, like 3 plus I is the set of all integers that give remainder 3 when divided by 5. Yeah. The set Z is the disjoint union of these classes, these 5 classes. Every integer is in one of these classes and only one, because when you know which class it belongs just by dividing it by 5, it will give you remainder 0 or 1 or 2 or 3 or 4, and you know, and you can put it in one of those 5 classes accordingly. The set of equivalence classes were denoted by Z mod 5, and that notation actually foreshadows the notation Z mod I. So in the present notation, that Z mod 5 should be called Z mod I, and I is 5Z up. See, I is 5Z up here. So what we wrote as Z mod 5 should be written as, in the new notation, Z mod 5Z. Okay, so this is the set with 5 elements, the 5 congruence classes, mod I. And we saw that we have addition and multiplication on this set. We can define an addition and multiplication on this set using the addition and multiplication on Z. Similarly, in the more general context, when you look at R mod I, the addition and multiplication of R will allow us to define an addition and multiplication on R mod I. And R mod I will become a ring with these new operations. And that will be called the quotient ring. We saw that we can define plus and dot on Z mod 5 and make it into a, turn it into a ring. And have a surjective ring homomorphism from Z to Z mod 5. And that will have a more general thing like that. We'll turn R mod I into a ring, and we'll have a surjective ring homomorphism from R to R mod I called the quotient homomorphism. Okay. That's what we'll